Let's get started with today's presentation, and we'll go to R and then we'll discuss a few things. Today's agenda item, we'll go over mainly things related to chapter 2. And although like this book was, the book that we are using was written a few years back, so obviously there may be few new things that have come up in R. So the codes that I will use today for exploratory data analysis or graphs and charts in some cases may be slightly different from what you may see in the book, but the book is still a good reference point. So we'll go over EDA, graphs and charts, data summary. I mentioned earlier also that the exploratory data analysis usually are done at two different stages during the data analysis process. One is towards the beginning. So before we undertake or select a proper statistical approach for statistical modeling, it is a good idea to do some exploration to understand what the variables are, how they are behaving through graphs and charts, and look at various things to get a better understanding to choose the right method. And once we apply a specific method for data analysis or statistical modeling, so even after that we may need EDAs or graphs and charts and some similar tools for few things like checking model assumption, whether the normality is being followed properly or not. So it has actually a purpose at two different places in this journey. So that's why this is an important topic. But many people have talked about EDA or data visualization in various contexts, and they have given a lot of good ideas. Especially this is a new book, Storytelling with Data by Cole. So what he says is, before we undertake any EDA kind of activity where we are starting exploration and mainly through data visualization, so understanding the context is very important. Like if it is business, then business context. If it is maybe medical related, then understanding that field or context where the data was generated is also very important, and that plays a very important role, and it will help a lot during the process, like how you attack that problem. And then choosing appropriate visual display. So as you know, like nowadays data come in so many different forms. We have numeric data, we have factor type of data, you know about like 4 scales of measurement, but we also have like data which is structured and data which is not structured. So we have data which may be images or which may be text data. It may be a combination of few things. So data come in so many different ways, and choosing appropriate tool or technique for visual display becomes important. And that's why like there's a saying in English that if the only tool you have is hammer, then every problem looks like a nail. So we cannot depend on only one way, our favorite way of displaying data all the time, like histogram or box plot. But we need to learn many different ways so that we can select the right one and most appropriate one given a type of data that we are dealing with. And in data visualization, it is also recommended that we remove or eliminate the clutter. If we are presenting some idea to a group of people, so it should be like a good visualization. If it contains too many unnecessary distractions, so it may not serve its intended purpose, and people who are listening or people who are being communicated certain idea, so that may not go across well if there are too many distractions. Focus attention where you want it. So in data visualization, your focus is on something. So it is important to convey that very clearly. Also think like a designer, like especially if you are using some kind of display to present your ideas. So you may have to think about like how do you organize it? How do you organize that information which is relevant and which get across people? And especially like this book, the book is about storytelling. So not only he, but there are many people who emphasize that when we are working with data, when we are doing data visualization, making graphs and charts, so we should be telling a story. Things should be connected, and it should lead to something, and especially like getting some insight, especially actionable insights. So sometimes we do things not for the sake of doing data visualization, but very often it should lead to something. And especially when you are presenting it in a nice connected way where you are telling a story so people can relate and see what's going on. There is another very popular person in the field called Edward Tufte, and there's a very popular book, and there are many examples of data visualization presented by Tufte. But what I have listed here is 6 fundamental principles of analytical design that comes from one of his books. So what he emphasizes is, so one of the fundamental principles is show comparisons, contrast, and differences. So when you are designing a graph or a chart, so it always helps when you can compare things and contrast and choose your colors, for example, or data visualization that highlight these things in a very easy way. Show causality, mechanism, explanation, systematic structure. His idea is that when we are developing any analytical visualization, so we should be able to include a lot of information which are related and relevant and that help to explain things. I remember like when I used to work at Ford Motor Company in Detroit. So when we made some kind of run chart of vehicle launches, and we were monitoring like how many warranty claims we get every month or every week. So whenever there was any design change, for example, or any action taken by like specific team, so we used to put an arrow and indicate that we did these things, so that it helps to explain what's going on. So for example, your chart is going at certain rate and suddenly you see a like sharp increase, and then you know that actually there was a design change which led to this increase, or there was a recall or whatever. So that make things easier for an audience to understand without much explanation. He also suggests show multivariate data. So usually like a chart which is based on one variable, we call it like univariate charts, may not be very informative in every situation. So his suggestion is to include like maybe bivariate or multivariate kind of data while designing any visualization. So show more than one or two variables. Just as an example, like in scatter plot, if you are studying relationship between variables, so you can plot 2 or 3 variables depending on the plot you are using. Completely integrate words, numbers, images, diagrams. So nobody stops you from including as much relevant information as you like. So not only like words or numbers, but he even suggests like images or diagrams if needed. Provide a detailed title. So title is very important, and it should be something that conveys the essence of your data visualization. And many times we should be able to indicate who are the authors, sponsors, what are the data sources, so from where this data was taken, show complete measurement scales, and point out any relevant issues in that plot. And finally, sixth principle is analytical presentations ultimately stand or fall depending on the quality, relevance, and integrity of their content. So a data visualization may look very fancy, very nice, but if it is based on data of questionable quality, if the data was not collected properly or if the data had issues, so very quickly that shine on that visualization fades away, and then people start asking questions, and then they understand maybe there was some issue with the data. Now we should be very alert. We should have a sharp eye when we are looking at any data visualization or any EDA tool that we are using. And some of the things we look for are listed here. This is not certainly an exhaustive list, but some ideas. So we certainly look for outliers. If there are data points which are very different from the main data set and looks very suspicious, it can stand out actually in very simple plots. You may have a box plot which covers almost 99% of the data, and anything beyond that is basically separated from the box plot, which indicates that these are maybe potential outliers, and they look like they need to be looked into further to understand whether they are genuine data or there was some mistake or error that happened while collecting the data. When we look at some visualization like histogram, we look for whether there is asymmetry of the distribution. So in situations where we expect a normal distribution, that bell-shaped curve, but if we get a double peak situation, bimodal kind of pattern or skewed distribution, so we need to look out for that, because there are many methods which depend on normality assumption, and if the variables do not follow that, if the assumptions are not fulfilled, then whatever analysis method we have used may have some problems. We also look for whether there are any changes in variability. So there may be a variable of interest which is a numeric variable, and there may be another variable which is a factor variable, and that factor variable may have like two different levels. It could be gender, like male, female, or it could be income level, or it could be some other factor level kind of variable. And if our variable of interest behaves differently in terms of variability at one level compared to another level, so we should be aware of that, and we have to see like how to address that. But we'll see how we can catch if any of these things happen. Similarly, clustering. So whether there is any groupings happening where data points gets like concentrated because of different reasons, and especially it happens when there may be another factor variable that is playing a role on the numeric variable in which we are interested. So one example I can give you is the data that we used last time, iris data. One of the variables there was species with 3 different levels, and if you look at a scatter plot between two numeric variables, you may find that those two are not related. But if you separate out the species, you may start to see that there is a pattern, and they seem to be related in some way. But clustering, we have to be careful, and non-linearity. So there are many methods like linear regression. So as the name indicates, it's based on assumption that the relation between two variables is linear. But if we plot the data and the data shows non-linearity, we cannot start using a linear regression method with that data. We may have to do some extra steps. So when developing a visualization, so I have broken that down into few steps. So usually if we are trying to work on a business problem, so we may have some question in our mind that we want to either verify or check using proper visualization. Statistically, we may say this is our hypothesis, that we expect that we made some change, and before change we had this situation, and after change we expect situation to improve. So whether it is like in manufacturing, it may be rejections. So a process may be leading to a lot of rejection, and then we collect data, and also we implement some solution, and we want to check what happened before and after. Or it could be new sales strategy that we want to check whether our actions are leading to improvements or not. So typically we start with some question in mind, we collect data, and depending on the kind of data and the business question we are asking, we have to choose appropriate visualization. So data could be of different types, and depending on the type of data, you may have to choose your visualization, because qualitative data may have one set of tools available, and quantitative data or numeric data may have another set of tools available to us. So once we choose appropriate visualization method, we may not be able to directly use it, because sometimes some extra work is needed, some data preparation, in some cases even data transformation. So those kind of steps may be needed before we can apply that method. And once we have the visualization, proper visualization done, we may develop insights and decide on next steps. And although these arrows are like going from one box to another box, but you can imagine actually a lot of arrows going back and forth. So it's never a linear process. So sometimes you come here and you feel that, oh, you need to go back to maybe data and again look at something and then decide about data preparation. So here is one example from manufacturing. I was involved with the data collection and also analysis, and this is maybe I think a bit old data, more than 20 years old. And this was when I was working with the consulting company, and we were helping a company to implement statistical methods. One of the areas they had a lot of problems with a key quality characteristic called end shake. And this is a critical characteristic for a component called plunger dial gauge. It's a measuring instrument that measures like small dimensions. So if end shake characteristic has a lot of variability, that will cause the measurements to be inaccurate. So because the purpose of any measuring instrument is to give you the right measurement, but if because of some quality problem, if it is not giving you the right measurement, obviously the actions you may take on that may be misleading. You may take actions where it is not needed, and you may not take action where actually it is needed. This characteristic had a specification that it should be within 850 plus minus 50, which means the end shake can go as low as 800 and as high as 900 and still be okay. So we wanted to conduct a process capability study, like we want to understand how capable is this process. And process capability is basically another name for understanding the variability in the data, how much variability exists in the data. So if the variability is less, we say process is more capable. If variability is high, we say process is less capable of meeting the requirements. And the requirements here are like 800 to 900. So there are certain guidelines like how we conduct this study, how this data is collected. So we followed all the practices and collected this data. And usually like these data points are one after the other. Like this is from the first plunger dial gauge that was made that day. This is from the second one that was picked up from manufacturing, third one, fourth one, and so on. But if you look at the data and we know what we want, what are the expectations, and when we look at the data, it may take some time for us to understand how this process is behaving. It will not be very obvious. Like, this is a small data set. I have fitted everything on one screen. So this is not even big data where we have like so many variables and so many rows of data, but this is just one variable and everything is on a screen. But still, it is not easy to pinpoint if there is any problem or not. The best thing we can do by looking at these numbers or staring at these numbers is that 837 seems to be the lowest value and 941 seems to be the highest value. So we know the range. The values range between 837, which is well within this, but 941 is outside. So we know that the highest value is outside, but the lowest possible value is within. But more than that, it's difficult to see what's the problem. But if we take the same data and make a very simple histogram, like this is a univariate situation, one variable, and histogram is a appropriate method for that. And if we not only make a histogram but also just include the other information, so you can see it has a title which doesn't say that this is just a histogram, but it says what it is: process capability study of and shake. Specifications are given, not only given, they are also actually drawn here. So this is the upper specification limit 900, and I have drawn them in red color because usually upper and lower limits are treated as danger marks for any manufacturing process. So the operator or the machine operator wants to be away but within the limits, and this is the midpoint 850. So when we look at histogram, we look at three things. First one is, where are the values concentrated? Where the values of this process are concentrated. And that we know that in this plot it is somewhere here, the bigger bars. So somewhere there we have the maximum frequency. Numerically, we can calculate average x bar. We can add all the values on the previous slide and divide by the number. What we get is mean. So in this context, mean represents nothing but the process setting, where the machine operator set the process. Because they have knobs on the machine, they can change the dimensions by rotating something or making some small corrections. Usually, the values will be concentrated where the setting is. So that's one thing we look at in a histogram. Where are the most values concentrated, or where is the central tendency? Second thing we look for is variability, like how much is the spread of this histogram. So we can see it starts somewhere here below 850 and goes up to almost like 950. It stops just before 950. So that's roughly the spread. And the third thing we look for in a histogram is the pattern. So what is the shape or the pattern? And in this case, we can see approximately, we'll never get a like perfect bell-shaped curve if we have data on like 10, 50 or 100 data points. So there will be some ups and downs, but more or less we can say that this data is coming from a normal process. There's no abnormality present in this process. Abnormality basically could be some special causes. So we can say that this at least process is not suffering from any abnormality, but everything seems to be normal. So that's looking at histogram. Now looking at the process, we know that this is the upper limit, and the place where it is, in a way actually it is dividing this histogram into 50-50. So what happens to those items that are more than 900? So this manufacturing process, what they have to do is they have to work on a rework. So they have to separate those items, and then they are reprocessed so that the value that are on the higher side can be brought into the specification limits. If they cannot be brought into the limits, then it has to be scrapped. So you lose that, you lose the dollars, you lose the time spent manufacturing them. One thing which stands out is why this histogram is shifted to the right, because there's a lot of room here, and if somehow the process was set not at 900 somewhere here, but slightly even somewhere here or here, still you could have accommodated a lot of more samples or bars within the limit, and you may have to do maybe only this part as a rework. They have a reason for why they do this. There is a context to that. There is a business context. There is a reason why they do something like that, because this is something they are doing day in and day out, and it is not for them, it is not something strange. It looks strange to us, like why they are behaving like this when they could have like more items which are correct within the spec and good quality. But here they are, a process which is very capable of meeting the requirement, they are creating 50% items totally reject. So one of the reasons they may give is, like in the machining process, if you have, let's say, a circular rod, and if you machine and reduce the diameter, and if that diameter goes below the lower limit, you cannot add the metal back and make the dimensions that were needed. But if you have something thicker, you still have a chance to remove extra metal and bring that thickness into the band that you need. So if the dimension goes below the lower limit, there's no rework possible, you have to just throw them away. But if they're on the higher side, you can still bring them in and rework. So it will cost a little bit more, but you can save that item. So obviously, between the red line on the left and red line on the right, this 900, those danger marks are not like equally dangerous. 800 is more dangerous financially because you lose more dollars, you scrap the item, and here you can rework. But other thing is like the fear is also unfounded because you have a lot of leg room. You could have done settings slightly below and still accepted many items, and your rework could have been reduced significantly. So instead of 50% rework, maybe a very smaller percentage. Now you see, like all those things that I was trying to tell and communicate is not possible by looking at this data. If I stare at this data for even 1 hour, 2 hours, I cannot like bring out that much information or extract so much information as I was able to do it by doing this simple chart histogram. So that's why like some people say a picture speaks 1,000 words. So if a person speaks at the rate of like 50 words per minute, so that person will take like 20 minutes for 1,000 words, and you show the picture, everybody is on the same page immediately. So a good graph, a good chart can do all that very quickly. So when we make a histogram, I said, like mentioned earlier, we look for the shape as one of the 3 things. One is central tendency, like concentration of values. Other is spread, and the third thing is the shape. So sometimes histogram may be shaped like this, symmetric. If you cut this histogram from the middle and fold on a piece of paper, they will like match because they are symmetric. So one feature of a symmetric histogram is that mean, median and mode are like approximately equal. I would not say equal, but approximately equal, because you cannot get a very perfect symmetric histogram. So a symmetric pattern also has another name. We call it normal distribution. Sometimes people call it bell-shaped curve because it looks like an inverted bell. So there is a single point of central tendency and the data are symmetrically distributed about the center. There could be situations where you get a skewed histogram. So this histogram has this tail on the left side. So because the tail is longer on the left, we call it left skewed or skewed to the left. Another name for left skewed histogram is negatively skewed. So on a graph paper, you have like negative values on the left and positive values on the right. So if the tail goes on the left side, then it's called negatively skewed. For a negatively skewed distribution, median is between mode and mean. You can see mode is the most frequent value. And in this case, it is towards one corner. And mean will be somewhere here, and median is going to be in between. Because median doesn't depend on the actual values, but it depends on how many values. It depends more on the count, but mean takes into account each and every information in data. To think of like any example where you can get this is, so maybe a very easy quiz. In a class, if there is a very easy quiz, so almost everybody scores very high. But there may be some people who may miss something or maybe did not study well. They may end up scoring low. And this is opposite of that. This is the mirror image of the earlier one. It's called skewed to the right because the tail goes longer on the right side. And again, median is between mode and mean, but the mean is now on the right. Out of these two, left skewed and right skewed, you may come across right skewed patterns more often. So this is seen more often, especially when it comes to like dollars, income, those kind of situations, you may end up seeing a right skewed distribution. So for example, if you think of a big company like Amazon, and if you have data on how much each employee in Amazon makes per year, so they have thousands of employees, and if you make a histogram, it may look like this, somewhat like this, where you have few people who make millions, a lot of money, and vast majority may be somewhere here. Or it could be house prices. So in a given area, if you have data on house prices, so you'll find that most of the houses in that area have like similar value, but there may be some houses which are like very, very expensive. So it will be positively skewed. It can also happen with the difficult test or quiz in a class. So because the quiz is very tough, majority of people score low, but then there could be some stars who did really well in the quiz and scored like even more than 100. So when we make these kind of visualizations, there are some rules that we need to follow. There is a grammar available, and especially in R, there is a package called ggplot2 which is very popular for EDA kind of work, exploratory data analysis, where GG stands for grammar of graphics. And this grammar of graphics has basically 7 layers. 1, 2, 3, 4, 5, 6, 7. And ggplot2 actually addresses this grammar of graphics very nicely, where you can make data visualizations in layers. You can address various things systematically one by one in layers. So there may be one layer where you are talking about the data, what data you are using, because a data set may be very huge. You don't want to use all the data to make a graphic. So you may have to filter out something, you may have to select some part, ignore others. But ggplot2 lets you choose data and tell through aesthetics how you want that graph to look like, what should go on x-axis, what should go on y-axis, what should be the color, or whether there should be any color. It also includes a layer for geometry. So what should be the geometrical shape in the graphics? So it could be you are just specifying that I want a histogram or a scatter plot or a box plot. So that we do by choosing proper geometry. It also allows you to do facets. You may be able to break out a plot as per like different levels of another factor. So for example, in iris data, if I am making histogram for sepal length, I may choose to do a facet wrap where I break the histogram into 3 parts. One histogram for the first species, another histogram for the second species, another histogram for the third species. So it allows you to do that. It allows you to do some statistics if you want to make a scatter plot and you want to include a linear model or non-linear model. It allows you to work with coordinates, like even x-axis, y-axis. Sometimes we may have to take a log scale because the data may be concentrated in one corner, but we want to spread it out. And usually people resort to some kind of transformation, like log scale transformation is very common. So that you can do very easily. It also helps you to choose various themes, like sometimes you just want your graph to be overall black and white, or overall like minimal design, minimal distractions. It has like some set themes that can be used. So ggplot2 allows us to basically implement grammar of graphics on which people have worked and help develop like useful visualizations. One thing is important to note is this grammar or the rules that we have, they are necessary for good visualization, data visualization. They are necessary, but they are not sufficient. So, for example, a simple sentence like, this dog is very cute. When I speak about it, when I read that sentence or write that sentence, everybody understands because I'm following the grammar. I'm not making any grammatical mistake. But so we can learn a lot about grammar, but that may not make us a good book writer or story writer. So that also needs a lot of imagination and other things. So following the rules, following the grammar is necessary, but not sufficient. It's just like driving, like you can read about all the possible rules when you are in high school by reading a book, but that doesn't ensure that you become a good driver also, because that will need a lot of practice. So rules may be necessary, but they may not be sufficient. You may still have to do a lot of practice to come out with good graphics. So as a univariate, with univariate data, histograms are very popular. One drawback sometimes you may see is that I make a histogram by hand, you make a histogram by hand with the same data, but histogram may be slightly different because I may choose the class intervals in one way, you may choose it slightly differently, and suddenly your graph is a bit slightly different from mine. So that can happen. But if you are only interested in looking at like what the overall pattern is, if you are like checking normality assumption, you may be more interested in the shape rather than other things. So in some situations, density plots become also very useful. For example, in this plot, you have histogram and density plots combined into one. And in fact, first one shows one peak, but second one shows two peaks. And when you have more than one peak in a histogram, that is an indication that some things are getting mixed. There's a mixture, maybe because of some background variable, maybe male, female, or different species, or some other thing which is mixing two different things into one. Similarly, you can even break these into different facets. You can do a facet wrap. So for example, in this case, I have separated out male, female, and different sites where this animal is found. Site 1, site 2, site 3. So there were, I think, 7 sites. When we study more than one variable, like 2 or more variables, correlations are very commonly used, and we are all familiar with the Pearson correlation. If we do this calculation and look at the correlation coefficients, so for example, this is 0.681 between D rat and MPG, we find that the correlation coefficient is 0.681. So it has a positive correlation, but it is very important to remember that Pearson correlation actually measures linear relationship between two variables. And looking at the number, we don't know whether relationship is linear or not. We can do fancy like tables like this or do all possible calculation. But these numbers do not tell us whether those two variables were linearly related or not. So for that, we have to see visually through maybe a scatter plot what kind of relationship those two variables have. So usually when we study relation between variables, we should not depend on numeric summary first. We should look at the visual summary first, and then only numeric summaries will make sense. So this is to remember that Pearson correlation only measures linear relationship. If you have nonlinear or asymmetrical marginal distributions, then it is better to capture strength of relation between variables using Spearman rank correlation rather than Pearson correlation. So it will not be correct to use the first method if the relationship is not linear. And similarly, if we have like a situation where same individuals are assessed by different judges, so there it is suggested or recommended we use Kendall correlation. So here are like some scatter plots. We can also like separate and see whether we really have linear relation or not. And usually we are looking for approximate linear. We'll never get perfect linear relationship in real life. Sometimes it may be a good idea to do marginal plots and see whether these two numeric variables show a normal pattern or not. We had used a psych package earlier, and at the beginning I think Kiran was talking about it. So by default, the correlation coefficient that you see in the upper triangle, by default it is Pearson coefficient. But you can also say method equals Spearman or Kendall and easily get other coefficients. For example, this plot here looks slightly non-linear between DISP and MPG. With Pearson, you have negative 0.85, but with Spearman, you can see the strength goes up because it captures the nonlinearity and gives you a higher value than what you would obtain by treating it as a linear relation between two variables. I'll go to Kaggle and then go to Notebooks and click on this plus new notebook button, and it takes you to empty template. I'm going to name this as week 2, and this will be available to you. If you miss anything, you have it here. And I'm going to remove this extra stuff. I'm also going to click on this on the right corner just to hide this extra stuff we don't need, to have some clean space. And if you click on view and theme, so right now it is light, and if you want to have it this way, you can even go for a dark mode. Let me write something in bold, week 2. And we'll need some libraries. I'm just going to type one by one. First one is the book library, and we'll use another one called MASS, and another one is DPLYR, dplyr, ggplot2 that I talked about. There's also something called ggextra. I'm also going to include correlation plot for one of the plots that I showed you. And maybe psych, and run so that it's available. So first let's have some data, and one of the data sets used in chapter 2 is named as POSSUM, POSSUM. I'm sure many of you know what is POSSUM, but if you don't know, if you just Google and look at images, this is how it looks. There are some cute possums also. So this is the data we'll use. We'll also look at the structure of possum. We can also run summary. Usual things that we do when we first encounter any data. So not a huge data set, 104 rows and 14 columns. A lot of numeric variables, but there are also some factor variables like POP, SEXX, and in terms of missing data, not much, only one variable, foot length. There is one data point. Actually, for age also we have two data points, which are NAs. Sometimes when you read data into R and look at the structure, you see that some variables are numeric, some are factor. So they are like automatically determined by R, but it may not be the case all the time. It may happen that you have a factor variable, but the values are in numbers, and R thinks actually it's a numeric variable and labels that variable as numeric. So one example is a site at which these possums data were collected. It shows a numeric variable, but these 1, 2, 3, 4 actually may be just the location 1, location 2, location 3. So 2 doesn't mean greater than 1, or 3 doesn't mean like 3 times of 1, and things like that. It may be a factor variable. But we'll use this data, and in the next block I want to show you how do you select. You have so many variables, but you may be interested in only some of them. So how do we select only part of it? So if you type name of the data and then type percentage greater than percentage. So in R, this is called pipe. It is a feature of a dplyr, dplyr. So what it does is it takes the input from whatever is on the left and passes that on just like a pipe to whatever is on the right. Later on you'll see that it becomes very convenient, especially if you have many variables and you are playing with some data, to use this format. So instead of all the variables, if I want to select just for any reason only first three, I don't want others, what should I do? So there is a function called select, and I can simply say 1:3, like I want first, second, third. That will give you first, second, and third variable. If for whatever reason you want first, second, and third, and also like 9th and then 10th to 13th, you can do it like this. So this select can be very handy if you only want to deal with one part of your entire data set. So what you can do is you can create your own data and call it like data1 and save it there. So when you run this, that gets saved in data1, and now you are dealing only with the subset of data where only those columns are available in which you are interested. Another thing we may have to do from time to time is we have to filter data for some percentage greater than percentage, and then if you want to filter, use a command or function called filter. So suppose I want to filter the original data in such a way that I only have data with the female, these 43 data points where we have only female values. The way we are going to do that is name of the variable and then two equal signs, and within quotation we say F for female. Why we use two equal sign is very simple, like one equal sign is same as this arrow in R, and people who use R usually prefer arrow, but you can do the same thing with equal sign also. You can assign anything to data 1 with equal sign 2. So equal sign is reserved for assignment, and two equal signs are actually equal. So that's the convention we'll use. So if you look at this now, this data frame has only 43 rows now, and you can see under 6th column you have only F values, no M. So you can filter out things very easily in R. Another thing we can do is arrange. Sometimes we want the data to be arranged in a particular way. So let me copy previous one and paste it here, and percentage greater than percentage. So I want to pass that on to the next one where I can arrange. Let's say in our output we want to arrange this variable called belly in a descending order. For descending we use DESC, and within parentheses we can say which variable. So we are saying belly. So if you run that, you'll notice that the last column, which is belly, is now in descending order, 40, 39, 38.5 and so on. Summarize. Let's copy this whole thing from the previous one and paste it here, and I'm going to add one more line for showing like how do you summarize something. So let's first type the function. The function is summarize. And suppose I want to summarize, I want to get numeric summary for this belly variable, and I want to get the average. So let's store the output of that in AVG, and we want mean of belly. Notice that the second line that I'm adding right now, at the end I should connect this to the next line using the pipe. We cannot leave it blank. Till here you are just finding the average. If you are just finding an average, this descending order has no meaning, so I'm going to get rid of that. So if you simply run this, you get the average based on variable sex, which is only for female possums, and the average for belly for that group is 32.8. But you can also find more summaries. You can put a comma and say, okay, I also want standard deviation. So the function is SD belly. So run that and you get two numbers now. You can also do comma count. So count equals, so usually for count we say n, which is the sample size, and then open and close parenthesis. Empty, you don't put anything there, and simply run. It tells you there are 43 samples. Okay, so that is summarize. Let me highlight another thing, way to handle or explore your data set. Group by. So for that I'm going to copy the previous entire code and paste it here and do some small modification. Add group by in the next line. So group underscore by. Let's group by. Remember we had a variable called site, like at what site this data was collected. So there were different sites. So let's group this by site and percentage greater than percentage. So connect it to this. Looks like there are 7 sites now, and because of group by, these averages are now separated out for each site, and you have the sample sizes, standard deviation and average values. If you like, now you can put another percentage greater than percentage and arrange them in whatever way you like, descending. Let's arrange these by standard deviations, so maximum standard deviations and so on. So you see now site 4 has possums with the highest variability in variable belly, followed by site number 5, and looks like site 6 has the lowest variability. Another function, like many times when you are exploring your data, you want to create your own new variable for whatever reason, and you can do that very easily with the function called mutate. We'll copy the previous part and after copying I'm getting rid of the filter. Let's have the entire data. Let's keep the count, but average and standard deviation I just want to have like one new variable, and let's call it TR for tail ratio. So tail ratio equals sum of, so there is a variable called tail, TAIL, and L, so tail length. So tail length, total of tail length divided by total of, so let's say the entire length of possum. So that should be total length, TOT. Let me copy and paste to avoid any error. Okay. So tail length divided by the total length. So we are calling that new variable as tail ratio. So tail as a ratio of total length. we'll arrange this as per TR. So the possums at site 6 have the largest or longest tails as a ratio of total length, followed by site 7, site 5 and so on. Okay, so now let me use that grammar of graphics that is implemented in ggplot2 and make some plots. So let me show you how you do that, starting with the histogram. So the base package in R also allows you to do certain plots, but ggplot2 is like much more versatile and lets you do many things very systematically, especially like those 6 or 7 layers. You can add them layer by layer. So we'll use our data possum and connect this to ggplot. So the function, although the package is ggplot2, the function is named as ggplot. If you recall, I mentioned that the grammar suggests that we should talk about aesthetics. So we use or implement aesthetics using AES, which stands for aesthetics. And basically we are saying what should go on x-axis, what should go on y-axis and so on. So we can say x equals, so let's do it for total length, I'm using this TOTLNGTH, total length, because histogram needs only one variable and we want to do it for total length. So we have defined aesthetics. One thing you can remember is whenever you have started this ggplot2 function, so before that you are using a package like using pipes, you may be using package like dplyr, but when you are making the plots starting with ggplot, you are adding layers. So when you are adding layers, we don't use the pipe symbol, we just use a plus sign. And then one of the things was geometric shape. So GEOM underscore histogram. So that will give you histogram for total length. So this is the default one. This is based on default setting. Obviously you can modify and do many things. I will add a layer for title, GG title. This is for distribution of total length, something like this. But if you put a comma in GG title and you want to add any more information like what is the source, so this is DAAG package. Like possum data is from DAG package, so that also will go as a subtitle. After x equals total length, if you want to include few more things, like what we can do is fill equals sex. So if you want to separate information as per one of the variables and run, so you get a stacked histogram. The red one is F and blue one is male. If you want to make the bars a little bit transparent, so within geometric histogram we can say alpha. So if you want to make it 50%, you can say 0.5, something like this. If you want to separate these two, let me copy this to new block and we add a layer here. So facet underscore wrap, and there you can say, so this has to be a factor variable obviously, so it will separate them into two different plots. See, instead of sex variable you can also try another factor type of variable, site. So depending on how many sites you have, it may get broken into that. I will also add one more layer just for the completion sake. In grammar of graphics I talked about theme. There are several inbuilt themes So let's say black and white, BW. So that plot looks like this. Okay, let's copy this whole thing just to show one more type of histogram pattern. And this time instead of facet wrap, we'll say grid. So instead of facet wrap, now we are using GRID. And inside this we have to say how you want to have that grid. So we can say VARS for variables, and let's have one for each. VARS site. So that will give you this grid. So first one becomes a row and site becomes the column. You can also do COLS, columns equal. So the columns are only for site. If you want rows, you can say ROWS, something like this. Let me copy this whole thing and paste it in a new box. And this time we'll talk about the density plot that I showed you. So obviously the geometric shape for density plot is different. So we cannot use histogram. We'll have to change this to density. So it will immediately give you visually whether male female data in different sites gives you very different total length or they are similar. Okay, let me copy this again. I want to combine actually histogram and density plot. Let's call it histogram plus density. So we have density here, and just before that I'm going to add GEOM underscore histogram. I'll keep alpha of 0.5, add a plus sign. So we want like two shapes. Let's see what we get. You may see this dark line at the bottom. So there is a density plot, but density plot, because it is between 0 and 1 and the actual values for the first histogram are between 0 and 6. So it's not really visible. The pattern is not really visible. We have to add few things here. For GEOM density, we can say aesthetics y equals, so we have numbers like up to 6. So I'm going to say 6 times dot dot count dot dot. So it will just count and use that. Let me try 0.3. In the next block, let's do scatter plot. So our data is possum, percentage greater than percentage, and then we want to make some plot. We specify aesthetics AES. We need x and y as numeric variables. So let's say on x-axis we say we have used tail length 2Ls on x-axis, and on y-axis let's say total and length was LNGTH. And for geometric shape, for scatter plot we say point. If you want to color the points, that we can do in geometric shape. When we say point, there we can say the color we don't want black, we want blue. Now if you want to add a trend line, so that will be a new layer, GEOM underscore smooth. So you want a smooth curve, you just say GEOM underscore smooth. So you get this curve. And by default, it uses a method called LOESS, and it tries to capture non-linearity. If you don't want this interval band or standard error around that line, you can say SE equals 0. and that will only leave the line. But even the line, you can choose a method. So let's say you want that line based on the linear model, LM. Let me copy this to the next box and say scatter plot with two lines or two trend lines. Here itself in ggplot, when we specify aesthetics x and y axis, there itself you can put a comma, and one you can say I want to color those as per sex variable, and you can put another comma and introduce one more numeric variable in the scatter plot by changing the size of the dots, where you can say size equals, let's say, I. So what this has done is it has introduced one more variable, and I is a numeric variable, so that's why the size indicates this number. So the highest one is 17 and lowest one is 13. As you start introducing like more variables into the mix, it will make sense to actually do a facet wrap and separate them out and look at them individually. Facet underscore wrap that we did earlier, we use this tilde and we want to separate this as per sex variable, so you get those two plots separated. If you want as per the site, so once you have the basic structure, you can do as per whatever variable that you are interested in. Let's do a scatter plot with log scale, but I also want to highlight why we are doing that. So first we'll have a normal scatter plot. So we'll use ggplot, and I'm writing this slightly differently than what I wrote earlier. Just to show you, you can also do this way. You can directly mention data here. You can say ggplot, and this time I want to use a data called animals, question mark and animals. If you run that, this data set is from mass package or library that we ran earlier, and it has brain and body weight for 28 species. So body and brain weight. So body weight is in kilograms, but brain weight is in grams. So that's the data we are using. So let's say on the x-axis we'll put variable body, and y-axis we'll put brain. So when you plot, this is what you get. This is actually same example that you have in the book. The problem is whenever you have a data set where the values range in a big way, like you have very small values to very huge numbers, your plots may not give a very useful information, like you may not be able to see certain things. There may be some patterns, but because of the scale, things get hidden. If you have a data point which is just like 1, and then within that same data set there are 10, 100, 1,000 different values, it can hide a lot of patterns within it. So that's where log transformation helps. So I'm going to copy this and paste it here and add scale for x, we want log 10. Similarly, scale for y axis, we want log 10. So this was the first one, and you see the second plot now in log scale brings the pattern between body and weight more clearly that we can see, which is not like as clear from this plot, because the variation within like small values, and because there is a big value here, so the patterns are getting hidden here, we are not able to see, but that gets much better visibility with log scale. And usually this we do with time series data, where the values over the years, let's say in stock market, changes a lot. I'm not talking about like a stock like GameStop, where things change actually within a few days, and it got everybody excited. But usually, like if you look at a company like maybe Amazon or Apple, so over last 10, 15, 20 years, you may see a better pattern if you plot it on a log scale. Let me go back to the place where I created that tail ratio thing using mutate, this table. So let's copy this part and bring it here. So we'll do the plotting for that. Just to recall, if you ran this one, you get like three columns. One is site, tail ratio, and count. So let's store this in new. So if you point an arrow towards new, this table will be stored there, and then we can make a bar plot based on the table that you see there. So we'll say ggplot for new data where aesthetics. I want to put this first column site on x-axis, but the problem is in the beginning you saw R treated x-axis as a numeric variable. In reality, site cannot be a numeric variable, it's a factor variable. So what we can do is, instead of saying x equals site, we'll say factor parenthesis site. So on the y-axis, let's put tr. We can also say fill as per the site. So for bar plot, we simply say col. So if you run this, you get a bar plot like this. Sometimes if you have many levels for a factor variable, let's say you have a data on like 50 states in US, and if you make your bars like this, it may become very crowded and it may be difficult to see what's going on. So what you can do is you can put the bars on y-axis. So either you can like switch the variables here, or you can simply say I want the coordinate coord underscore flip. Next one, I want to show a box plot, and for this one I'm using possum data and connect it to ggplot with aesthetics. So let's say on x-axis of this box plot I want the variable sex, and on the y-axis I want the variable chest. We can also like differentiate the color with a factor variable, and for box plot you can simply say the geometric shape underscore is box plot. So we have to have a plus sign. You get the box plot very nicely. So there's another way, let's call it box plot interaction. So instead of using only one variable, like sex is male, female, if you want a combination of two factor variables, that also you can do very easily using ggplot, and we'll call it interaction box plot. And how do you do that? You simply say x equals interaction and parenthesis, and then you mention which variables. You simply list them and run your box plot, and suddenly you have all possible combination of two variables. So for example, this is site 1 female, this is site 1 male, this is female, male site 2, and so on. So in a box plot, this is the minimum value. You may have some dots or data points even below the minimum indicated by box plot, and they are treated as outliers. They are beyond the 99% rule that box plot uses. This is the first quartile, the middle thick line is the median, and this is the third quartile, and this is the maximum value. For female and site 1, there is likely one outlier on the higher side, and there are likely three possums that seem to be outliers on the lower side in terms of variable chest. And it gives you some idea about variability in the data. If you look at the box plot that has the maximum spread obviously has more variability compared to others. So for example, this box plot here, this is like female and site number 3. Spread is much smaller than female and site 4, where you can see there are possums with smaller chest values and large chest values. But the idea is you can get interaction also very quickly. We'll use ggplot, and this time we are using another data set called cuckoos. You know, like cuckoos lay their eggs in another bird's nest, and there are people who feel that when they lay eggs in another bird's nest, they also try to match the size of the eggs of that bird. So basically this data was collected to test that. So cuckoos are very smart. If they are laying eggs in a bird's nest whose eggs are small, they tend to come out with the smaller egg. And if they are going to a nest of a bigger bird, they lay eggs so that that bird is not able to figure out it's not their eggs. So this is an interesting data set. AES, on the x-axis will put length and y-axis will put species. We want a scatter plot. So this is how it looks like. So these are like different birds whose nest are being used by these cuckoos. So because wren's eggs are smaller in length, so cuckoos tend to have a smaller egg. So there is a variability, very visible variability. And you can capture this like probably more easily using a box plot. So I'll not call it plot in two columns. Let's say just plot. So you can see this highlights things more easily. Like in a box plot, you can do the comparisons. So clearly this wren versus this sparrow, hedge sparrow, the overlap is really very small, only little bit overlap in the upper tail and lower tail. The last plot that I want to show is marginal plot. I'm going to copy a scatter plot that we did earlier, and then we'll create marginal plots on both sides. And let me save the output by putting an arrow sign in P, and then we'll use that P in a GG marginal plot. Simply run this, you'll see it plots marginal plot. You can always put some color. We should say fill, pink. Although the default is a curve, but you can also say I want a histogram, something like this. Okay, I think I should probably stop here. I'm going to save this by clicking save version and click save, and I will make the link available to you so that if you missed anything you should be able to see the code. Okay, then I'm going to stop here and I'll see you next week.
Thank you. Bye bye.
Thank you.